Okay, so we're about to start the curve sketching section in the next video. But before we start, I wanted to make this video to summarize the main points that we've learned so far in Chapter 4. Chapter 4 being applications of differentiation. And the reason why I want to do this review is because I think it's really important that you have a solid intuitive understanding of curve sketching with calculus. And the reason is because, in my opinion, what you need to understand in order to curve sketch with calculus is highly relevant as far as you being able to apply calculus in your respective field, whether it be chemistry, biology, physics, engineering, business, at least from the calculus 1 perspective, so differential calculus. So once you finished calculus 1, assuming you learned it well, you didn't fail it, and so you understand the basic concepts, then definitely the most valuable kind of tool you've gained is everything we learned in Chapter 3. So you can take a function or an equation, find its derivative, and then plug in any x value you want to get the rate of change of that function or equation at any point you want. With what we learned in Chapter 3, you can do that quickly and easily. If you can do that, as long as it's not just totally blind, like you have no clue at all what you're doing when you're taking the derivative and what it means, as long as you have at least some understanding of what it means, then that's the most valuable skill, applied skill that you get from differential calculus, for sure. But the second most valuable skill, in my opinion, is all of the intuitive knowledge that comes with knowing how to curve sketch with calculus. Now, you might say, well, when are we going to sketch a curve, sketch curves in practice? And, you don't sketch curves in practice. Yes, you're right. But in order to sketch a curve, what you're going to see is, as we go through this, if you can analyze and sketch a curve from all the different angles we're going to talk about, then you have a mastery of analyzing how the function or the equation behaves. So from that sense, if you imagine in real life, the function or the equation is going to mean something from an economic standpoint or a physics standpoint or a biological standpoint. So if you can sketch the curve in practice, you might not actually sketch the curve, but you might use a lot of the techniques that we use in curve sketching to analyze the function. Think about what it means in real life. If it's concave upward in a certain region, well, from an economic standpoint, that means more people are coming in, because of the holidays or something, or there's some factor. If it's increasing at an increasing rate, things like that. Okay, so this is really important. Applied differential calculus, just taking general derivatives, curve sketching, and then in third and fourth, I would say, is related rates and optimization problems. We haven't gotten to optimization yet, but okay. So what have we learned so far in Chapter 4? So let's say we have a function. And we're just going to focus on functions at the moment. And the reason is because if we had a relation, like something like a circle, everything we're going to talk about in curve sketching, in this video in curve sketching, you can still apply that to relations. It's just a little different because each x is going to have like two possible slopes, two possible curvatures, things like that. So for simplicity and for the sake of analysis, we're going to focus on functions. And so what we've talked about is that the main idea is we've been given an interval. A closed or open interval, or partially closed, partially open, and then there's some stuff going on in between. And actually, usually the interval is closed. Okay, so with a closed interval, if we want to analyze this, okay, let's say we can't see the graph or whatever. Maybe we can see the graph, maybe we can't, but we just want to analyze this with calculus. And even algebra as well. We're going to bring algebra in when we get to the curve sketching section next, in the next video. Well, okay, we can first think about the endpoints. If it's a closed interval, then you can just evaluate the function at that x value. Like, this is f of x, right? This function. Just put in f of whatever this is. X left, like left endpoint, and x right. F of xl, f of xr. Okay, but what if one of the ends is open, one or both of the ends is open? Well, you can think about it this way. You could take the limit, if this is x r. You could take the limit as x approaches xr of f of x. That's just one way you could look at it. Again, I don't know what you would do with this, but you can, that's how you can analyze like a real life function. You can use limits. All right, now what if it's not an interval? It just goes, the domain is all real numbers on one or both ends. So there's no endpoints. Well, you can look at the endpoints like you could analyze, this is f of x. You could see what is the limit as x approaches infinity of f of x. That's like the endpoint. Just to get an idea of the end behavior. This might equal infinity. That's fine. If you're sketching it, then you'll sketch the endpoint or something like that. But even if this is a real life function, that's just okay. That's information. As x goes to plus or minus infinity, the function is approaching plus or minus infinity. Okay, so that's the endpoints. That's how you can analyze the endpoints. But what about between the endpoints? So if you had a function going off to plus or minus infinity, just imagine we're just anywhere in between, just kind of in the midst of the function. We can bring back an actual, let's actually put some endpoints here. Okay. So what do we do in away from the endpoints? What have we learned about analyzing functions? Well, probably the first thing we would do is find the critical points. And so I've got a continuous function drawn here, but everything I'm talking about right now is completely general. You could have absolutely anything in between here. Maybe we don't even know what it is. It could be anything. I'm talking completely general. So you analyze the endpoints, and then from there, in between the endpoints, you could find the critical points. What are the critical points? That's going to be anywhere away from the endpoints. You can't have a critical point at an endpoint. So anywhere away from the endpoints where the first derivative either doesn't exist or it's equal to zero. Absolutely anywhere. So this could be at a discontinuity. It's anywhere where the derivative doesn't exist or the derivative is equal to zero for any function, no matter any type of function, no matter what it is. Okay, now you could also think about doing this same thing with the second derivative. There's no name for like critical points with the second derivative, but as far as analyzing a function, you could kind of think of it that way. Maybe you could call it like the second critical points. I don't know. There's no official name, but yeah, I guess the second critical points. So you take the second derivative and find the points where the second derivative doesn't exist and where the second derivative is equal to zero. Whether or not the function is a continuous function or not doesn't matter at the moment. All right, now what you could do from there is one of the things about critical points, first, or we'll think about the second critical point, second derivative critical points as well. This applies to both. The thing about critical points is that the only way a first derivative or second derivative can change signs is when it crosses over a critical point. There's no other way for the first or second derivative to change signs unless it's crossing over a critical point. And so obviously if let's say the simplest case where the first and second derivative both exist, it's a continuous function and they both exist. Well, in that case, the first and second critical points are going to be where the first and second derivative are equal to zero, and that's how it's continuous, and that's how it crosses over. It has to go from positive to negative or negative to positive. You have to go through zero. Okay, now let's say you have a continuous function, but perhaps the first or second derivative don't exist. Well then, okay, the first derivative is something like this. This is the function, but you can imagine when you take the first derivative, the first derivative is going to have a jump discontinuity because you all of a sudden you go from this slope and then you just jump to this slope. But that is a change in sign. And similar idea with the second derivative. If you're wondering what kinds of functions do things like this, well, an absolute value is something like this. But then when you get to when you get to some of the fractional exponent, like x to the, if you did 8x to the 8 thirds, then the derivative of that is x to the, it's still greater than, the exponent's greater than 1, and then f double prime doesn't exist at x is equal to 0. So like right now, you can plug in x is equal to 0 and get something. If I took the derivative, 8/3 minus 1 is 5/3. So I get x to the 5/3, and I can still plug in x is equal to 0, but f double prime of x, now 5/3 minus 1 is 2/3. Now, well, I could still plug in 0, but if I go again, yeah, if I started with x to the 5/3, it would be 5/3, and then f double prime of x would be minus 1/3 x. So now I can't plug in x is equal to 0. I'm dividing by 0. It's like things like that, right? The first derivative exists at x is equal to 0. The second derivative doesn't. Okay, but even like a discontinuity, if you went, you come in negative, and then you jump here, that's a critical point, and you change signs. You go from a negative slope to a positive slope. And you could think of a similar idea with concavity. Okay, so once you have the first and second critical points, then you can analyze where the function is increasing, decreasing, concave up, and concave down. Because since it can't change signs in between the critical points, you can just plug in a number, plug in an x value within each of those intervals and see is it positive or negative, and now you know. All right, now how else can we analyze in between the endpoints? Well, there's local maxes and mins. Local maxes and mins are associated more with the first derivative, but if you want to think about a parallel for the second derivative, the parallel would be inflection points. Okay, now just note that a local max or min can be at a discontinuity, but an inflection point can't. If it's a discontinuity, there can be no inflection point. So what's a local max or min? Well, you can't have a local max or min at an endpoint. Neither can you have an inflection point. So there's a left and a right side of a local max or min or an inflection point. But a local max or min is if you've got a function and you take any open interval anywhere on the function, any open interval, and the key word here is open. It has to be open. And if within that open interval there is a unique point or points that are either greater than or equal to all the other points in the interval or less than or equal to all the other points in the interval, then that's a local max or min. You could have multiple local maxes or mins, so every point here would be a local, but then like this interval, every point here would be a local max. But in general, most of the time, it's like 1 point is the local max or min. Now, the key word there is an open interval. It has to be open, because otherwise, if it could be closed, then I could do this. I could draw a closed interval here, and then this point, the point on the interval, would be a unique point that's greater than or equal to all points in the interval. So that would be a local max, but we don't want, that's not a local max. This point doesn't mean anything. So the way it's defined is it's defined this way, open, because now there's no unique point, because it's not defined at the interval. So like it's not a unique point. You could take the limit as x approaches this interval from the right, but that's besides the definition of local max or min. There's no unique point. You can't specify a unique point. So there is no in this interval, there is no local max or min. But this open interval, there's a local max. There's a point here that's greater than or equal to all of the other points in the interval. And again, an endpoint, you can't specify an interval around it. So there's no local maxes or mins at an endpoint. Okay, but you can have a local max or min at a discontinuity. In this case, take the definition. I specify an open interval. around in any open interval? Is there a point, a unique point or points that are greater than or less than or equal to all other points in the interval? Yeah, this point. That's a local min. That's a local max. That's neither. There is no local max or min, because this here you can't specify a unique point, and you might say, well, is this the local min? No, you can't specify a unique point. It's undefined, or it's defined here. Okay, now what about an inflection point? Is there some similar, definition for an inflection point? No, there's no definition like open interval and the function does something that makes an inflection point. But the way you test for a local max or min with the first derivative, the way you test to see if there is a local max or min using the first derivative is the same way that you're going to test to see if you have an inflection point using the second derivative. All right, now note though, the names are to test for the local max or min with the first derivative. That's called the first derivative test, and then there's something called the second derivative test, but that's actually has nothing to do with testing for the inflection point. The second derivative test is an alternative way to test to see if you have a local max or min. There is no official test for the second derivative like that has an official name to it. But the idea is for a local max or min or an inflection point, if the first derivative changes signs as it crosses over a critical point, then it's going to signify local max or min. And similar idea with if the second derivative changes signs going over a critical point, then that's going to signify an inflection point. But okay, let's get into specifics on this. The first thing to note is that the first derivative test, and it's not called the second derivative test, I guess the inflection point test with the second derivative. So the first derivative test and the inflection point test using the second derivative, these only apply for continuous functions. So first of all, you can't have an inflection point at a discontinuity. So obviously that applies only for continuous functions. But we just saw you can have a local max or min at a discontinuity, but in that case, you can't use the first derivative test for a local max or min at a discontinuity. That won't work. You might get lucky and it works, but you just got lucky. It could have just easily not worked. So you can only use these tests on continuous functions. Now, it doesn't mean that the first derivative has to exist or the second derivative has to exist. I didn't say that. So for like something like this, first derivative doesn't exist here, you can still use the first derivative test to see if you have a local max or min. This would be a local max, right? You could draw an open interval. There's that unique point that's greater than or equal to all points in the interval. And a similar idea with the test with the second derivative. The function has to be continuous to have an inflection point, but that doesn't necessarily mean that the second derivative has to exist. The second derivative doesn't have to be continuous. The function has to be continuous to have an inflection point. The function doesn't have to be continuous to have a local max or min, but to apply the first derivative test, the function has to be continuous. So what's the first derivative test? This is a test to see if you have a local max or min. The first derivative test is that if the function is continuous, and then now with that continuous function, you have critical numbers at points of continuity. So a critical number could be where the first derivative equals 0, but you could also have a first derivative not exist here and it's still continuous. That's a critical number. If the first derivative going across that critical point changes sign, then you have a local max or min. If it goes from positive to negative, then it's a local max. And you could think about it this way. Positive slope, then it switches to negative slope. That's a max, right? Positive slope, switches to negative slope. That's a max, right? And then vice versa, if it goes from negative to positive, then it's a local min. If the derivative doesn't change signs. So if the critical point, the derivative equals 0, like that, or derivative doesn't exist here, but it doesn't change signs, then that tells you that there is no local max or min at that point. It's not that it's inconclusive, it's telling you there is no local max or min. Okay, now before I talk about looking for inflection points using the second derivative, let's quickly talk about the second derivative test. This is the second derivative test. That's the name of it. This is an alternative way to test to see if you have a local max or min. So here, if you look at the theorem, it says that f double prime needs to be continuous. And all they're saying there is that, again, doesn't mean the function. They're not talking about the function. They're saying f double prime. They're saying the second derivative has to exist. If the second derivative doesn't exist at the point of interest, then you can't use the second derivative test. Okay, now since the second derivative exists, the first derivative is also going to exist, which means that since it's a critical point, the first derivative is going to be equal to 0. Because if you had a point like this, that's a critical point, and if you want to do the second derivative test, well, the second derivative is not going to exist. The only way the second derivative is going to exist is if the first derivative exists. If the first derivative exists, if it's a critical point and the first derivative exists, that means the first derivative is equal to 0. So the first derivative is going to be equal to 0. The second derivative exists. If the second derivative is positive, meaning the curve is concave up, it's a local min. If the second derivative is negative, it's concave down, that means it's a local max. If the second derivative is equal to 0, then the test is inconclusive. So this doesn't mean that there is no local max or min. For this case, that means that it's inconclusive. This is different than if you use the first derivative test and it doesn't change sign going across the critical point. Then it's telling you there is no local max or min. For the second derivative test, if f prime is equal to 0 and the second derivative is equal to 0, then it's inconclusive. So what do? Well, you can go apply the first derivative test. You could pick either one of these. You can pick. All right, now the inflection point, though. So we see how we can test for a local max or min. Now we want to test for an inflection point using the second derivative. This is not the second derivative test. Well, again, it's kind of paralleling the first derivative test, but now using the second derivative. The function is continuous and has to be continuous. The function has to be continuous at that point because otherwise there is no inflection point. But the second derivative does not have to exist. And even the first derivative doesn't have to exist. I don't even know if that's possible, how you could have a continuous function. Yeah, around the point, you're going to have the second derivative exist, or else there's no inflection point. But at the point, the function has to be continuous. But technically, the first or second derivative doesn't have to exist. But it's not necessarily a critical point either. It's a second critical point. From the perspective of the second derivative, it's a critical point, but it's not necessarily a critical point with respect to the first derivative. So remember, in the beginning, the idea was we calculated the critical points with the first derivative and also with the second derivative. For an inflection point, it's going to be the curve has to be continuous at that point, and it's going to be at one of the second critical points, but that doesn't mean that it's at one of the first critical points. So we've tested for the local maxes and mins, and we've come back. And now we want to test for inflection points. We're testing all of the second critical points. We don't care about the first critical points. The first and second derivative test, we were testing the first derivative critical points. Now the test with the looking for inflection points with the second derivative, we're testing the second critical points. And I'll say it again. You could have an inflection point and it not be a critical point with respect to the first derivative. Okay, so what's an inflection point? If the concavity changes signs across the point, the second critical point, then it's an inflection point. If it doesn't change signs, then it's not an inflection point. That's it. There's not like, okay, if it changes signs, there's one kind of inflection point. If it changes from concave up to concave down versus concave down to concave up, it's an inflection point. It's just called an inflection point. And we saw when we went through the text section 4.3 in the textbook how you can have at that point the second derivative doesn't exist and it's still an inflection point. So I'm saying it's not like it has to, for an inflection point, you have to go through f double prime is equal to 0 to have an inflection point. Not necessarily. Okay, now what about at a discontinuity, like a local max or min at a discontinuity? Is there any test for that? What if there's a situation where for some reason you just can't, I don't know why, but you can't use the first or second derivative test or the inflection point test with the second derivative? Well, you could think about like the idea of doing this in a numerical way. So, let's just look at, if this is like an this is where the first derivative or maybe the second derivative is equal to 0, but it's not an inflection point. Or no, this would be an inflection point. This wouldn't be a local max or min. But so if you wanted to inspect this area, what could you do? Well, you could, all right, this is f of x. You could go into Excel or go into MATLAB or any software, and you could make a big column. And if this is the interval from, -3 to 5, let's say, then you start at -3 and then you go -3. Then the next row is -2.9, -2.8, -2.7, -2.6. You could make it even finer than that if you want. You could go -3, then -2.99. You could go as fine as you want, all the way to 5, and then go to the next column and type in the formula for the function, and then drag that down, and then you could visually look and see what's going on around that region. Is there a number that's lower, that's less than or equal to every other number in that area? Or you could check the concavity as well. Evaluate you could take the second, you could put one column as the function, the other column is the derivative. So evaluate the derivative and then just populate the x values into the derivative function. Same thing with the second derivative, and just analyze it. See what numerically, is there any local maxes or mins? Is there truly a concavity switching signs? Like, how is it behaving? Like, look at I'm not saying graph it. I'm saying look at the numbers. Look at the literal numbers. And like with it, you could do the same idea with a discontinuity. We talked about how you can use if-then statements to program piecewise functions or discontinuities. Put the interval of the x interval, and populate the function, and just take a look and see that there truly is this one value, because you'll have the if-then statement will say if x is equal to the value of the discontinuity, put this. You can take a look and see. Okay, now before I end this video, I want to point out another thing. I want to point out is that, so if you have any kind of function that does anything weird, or maybe a discontinuity here. Okay, I mentioned at the endpoints. One way you can analyze endpoints, if it's an open interval, is you could take the limit as x approaches the endpoint here from the left, and just to get a sense of what kind of this value is. Well, you can take limits anywhere in the middle of the function, and not just that, you could take limits of the derivative as x approaches something, or of the second derivative. So you could say, what's the limit? This is f of x. This is f of x. You could say, what's the limit? And this is x1. What's the limit as f prime of x approaches, the limit as x approaches x1 from the left of f prime of x, to get a sense of the slope. Or you could do the same thing with the second derivative. Like, if you were graphing this, if you want to do a really good graph, you might want to get the limit, take the limit as f prime of x, f prime approaches x1 from the left, and you want to draw an accurate slope. But I mean, besides that, in other words, you could do a really good curve sketch that way. But besides that, if you're just analyzing a function, you can take limits with the first or second derivative. It's same with a discontinuity. You could take the limit coming from here, the limit coming from here. If you had maybe you had a max, there's a function that's doing like this, and then it comes here, and then this here isn't this isn't a global max, right? If this is the entire function, let's say this is the entire function. That's not a global max, because it's not defined there. It's not closed. But you can certainly take the limit as x approaches this value, and get a sense of, okay, that's technically not by definition a global max, but if I take the limit, I could call that kind of like the global max, right? If it was like this is the entire function. X, this is another f of x. This is the entire function. That's technically, by definition, if that's an open circle, that there's no global max. But if you want to get a sense of it, you could take the limit as x approaches here from the left and see, okay, and well, that's the global max, kind of, quote unquote. So you can use these limits on the function at the endpoints or anywhere in between, at discontinuities, even at non-discontinuities. You could use these limits on the function or the first or second derivative. Give you all kind of information about the function. Okay, so I think with that, we're ready to start curve sketching.